So welcome to Unit 4. In Unit 4, we're going to be studying energy and thermodynamics. And there's some laws of thermodynamics. One of them is enthalpy that we will talk about. So far in our study of chemistry, we have looked at matter and changes in matter. In this unit, Unit 4, we're going to be looking at changes in energy. And so the first thing you need to know is, what is energy? Well, energy is very simply the ability to do work. And there's 2 to 3 main types of energy. Depends kind of how you look at it. We have potential energy, kinetic energy, and radiant energy. Now, I'm sure you're probably familiar with these things from your previous studies, even probably in elementary school. And so we're going to take a look at the different kinds of energy. So let's first kind of access what you already know about that. So I've got 5 quick questions for you. The first one is, what type of energy does this ball have right here? It's sitting there in the girl's hand. Would it have potential energy, kinetic energy, or radiant energy? Just jot it down and we'll take a look at them in a second. How about this water in this wheel? Apparently we used to have tons of these on Delmarva. We don't now. What type of energy does that water have? How about the third one? Look at the water in this dam. What kind of energy does it have? And the arrow here in the bow, what type of energy does it have? And take a look at the sun. What type of energy would you say it has? All right, so what'd you say for this first one? Those were my 5 quick questions accessing your previous knowledge. If you said potential energy, you're exactly right. The ball is still. It has the potential to do something because of its position, but it's not doing anything right now. Whereas the water here in this wheel, hopefully you said kinetic energy because this water is moving. What about the water here for this third question? Hopefully you said potential energy. It has the potential to move and do work, but it's not currently doing that. And the arrow here in this bow, hopefully you said potential as well, because it has energy stored due to its position. And this type of energy here, when you're looking at that sun, hopefully you said radiant energy or light energy. All right, and so let's get into some vocabulary words. First of all, as we're looking at energy, we're going to measure it usually in joules, kilojoules, or calories, or kilocalories. And the types of energy, again, potential, kinetic, or radiant. Sometimes radiant can be put in kinetic because you'll remember that all light energy comes from those electrons falling back down in their energy levels after they've been excited and jumped up. And so here's just a few pictures here. You can see this rock here has potential energy. There's some radiant energy from the sun, and the kid on the skateboard has kinetic energy because he's moving. So as we're measuring energy, and that's what we're going to be doing in labs during this unit, we're going to be studying how energy moves from one object to another, and that's called calorimetry, and you're going to be using a calorimeter in a virtual simulated lab this week. We're also going to look at specific heat. Specific heat is really something you already know about because we live close to the beach. And so if you go to the beach on a hot sunny day in the summer at 3 o'clock in the afternoon, what is hotter, the sand or the water? Yes, the sand will burn your feet off, and that's because it has a low specific heat, which means that it doesn't take a lot of energy to heat it up. Whereas the water is cooler because it has a high specific heat. It takes a lot of energy to heat the water up. So we on Delmarva know that a great time to go to the beach is in September because the water is still really warm. And it's because of that high specific heat, because it takes a lot of energy to warm up the water. And so the water doesn't get warm until it's September, really. And so the symbol that we use for specific heat is C. And you will need to know the specific heat of water. Like I said, it is high. It has a specific heat of 4.184 joules per gram degrees Celsius. Calories are another way that we measure energy, and I'm sure you're familiar with that with food. A calorie is 4.184 joules, so you'll probably want to know that as well. A calorie is also, and you don't need to calculate joules to get calories, because calories are quite simply the amount of energy to raise 1 gram of water 1 degree Celsius. Now, the thing is that's not a lot of energy, and that's how we measure our energy in food. So what they did many years ago is they agreed to measure all the energy in our food in actual kilocalories. So when you look at a label and you see it has 400 calories in it, that's actually 400,000 calories. Food calories are kilocalories. So just so you know. And we get that from our carbohydrates, our proteins, and our fats. And you do need to know those numbers, that a gram of carbohydrates is 4 food calories. Those are kilocalories. A gram of protein is 4 food calories. And that a gram of fat is 9 food calories. Now, we're not putting kilocalorie there because we're putting that capital C. So pull any food label, and when you look at it, you'll see that capital C because it's really kilocalories. All right, and so when we start to take a look at thermodynamics, the idea of how energy is involved in our chemical reactions, the first law is that, of course, we can't create matter or destroy it, or energy for that matter. And so essentially the energy in the universe is constant. A way to take a look at that is this, and you'll do this week in the lab, and I'll talk about this more on Tuesday evening, is a calorimeter. And this week using the calorimeter, you're going to put some hot metal in there, and the hot metal is going to lose energy. And essentially we use lose, that word loosely, because it's not really losing energy, it's just transferring it to the cool water, and the cool water heats up and gains energy. And this is what we would consider thermodynamics. And so really energy isn't really lost or gained, it's just transferred from one object to another, because again, the amount of energy in the universe is constant. So nothing is losing energy or really gaining energy, it's just moving. And so how does the energy do this? Well, that's because energy is the product of the amount of heat done and the work. Not an equation that you're going to need to know, but this is an equation that you're going to need to know. And Q, again, is the quantity of heat, where C is your specific heat, M is your mass, and your delta T, that triangle T, is your change in temperature. So you find that by doing a final minus the initial temperature. And every substance, just like the sand and the water at the beach that I talked about, has a different specific heat. And here are some of those specific heats. You can see that water is really high. Something like steel heats up very quickly, is low. And as I mentioned already, you do need to know that. And so we're going to use that formula to figure out how much heat would you need to raise 50 grams of steel, to take 50 grams of steel and raise its temperature 50 degrees Celsius. So how would you do that? So again, always looking at what's given in your problem. So we have 50 grams of steel, and we want to change its temperature. It's delta T, in other words, 50 degrees Celsius. And so you would start with the formula, which is that the quantity of heat equals the mass times specific heat times your change in temperature. And in this case, we're changing the temperature of steel, so we would need to look at the chart and get the specific heat of steel. So we'd simply take that mass, substitute it in, 50 grams, the specific heat of steel is 0.45, times our change in temperature. And so it's really just a plug and chug. 50 times 0.45 times 50, and you're going to get 1,125 would be the quantity of heat energy you would need to change that. And of course, 1,130 rounded to 3 significant figures. Pause the video and see if you can do this next one. So once again, hopefully you use that formula. You looked at what you were given. Once again, you were given 50 grams of water, and you wanted to change its temperature 50 degrees Celsius. So you could probably already guess that that number is going to be higher than the quantity of heat needed to raise the temperature of steel. And so simply plug those numbers in, and you're going to need 10,460 joules of energy. That's our quantity of energy to change the temperature of the water. And then I would need to round that to 10,500 is what we would need to round that to have only 3 significant figures. I left 4 significant figures in there, but you would want to round it. As we finish up this with this video, here's a couple of videos and simulations that I would encourage you to take a look at. So I'm just going to leave this here on the screen as I end this video, and we'll pick right up here on Tuesday at 4 p.m. I'm looking forward to seeing you, and I hope that you guys have a great rest of your weekend and into next week.